All right, IBAASL2. Today we're going to talk about independent and dependent probabilities. So first of all, the definition of independent. If two events are independent, if the occurrence of one does not affect the other. Examples of this would be like, if you roll a die and then flip a coin, what's the probability you get a heads and then a 5 or something like that. The coin flip or the die roll doesn't influence the probability of the other thing changing. So if you want to find the intersection, like of two things happening at the same time, the probability of A and B, it's just the probability of A times the probability of B. You just multiply their respective probabilities together. We're going to illustrate this property with an example about a bag containing red and white balls. So the first bag has 3 red balls and 2 white balls, and then a second bag has 1 red ball and 4 white balls. A ball is going to be selected at random from each bag. Find the probability that both balls are red. Well, the probability of a red, what notation do I want to use here? Hold on. Yeah, so the problem, I think that the notation they use in the book is like red 1 intersection with red 2. These are independent probabilities. So you getting a red on the first bag doesn't change the probability of you getting a red on the second bag. So you can just take the probability of getting red with the first bag and then multiply it with the probability of getting red on the second bag. So red on the first bag is 3 out of the 5 total balls in that bag, and then on the second one is a 1 out of 5. So the probability of getting both reds are 3/25. Just multiply straight across. Now, the probability that the balls are different colors. The problem with this is that there's multiple ways this can happen. I mean, different colors means 1 red and 1 white, but it doesn't denote which order that happens in. It could go red, white, or white, red. So, in general, you have to figure out the red-white probability and then add the white-red probability to it. So I guess using their notation, this would be probability of red 1 intersection white 2 plus the probability of that would be white on the first bag, white 1 intersection red 2. So let's see, getting a red then a white is going to be 3/5 on the first red, and then a white on the second one is 4/5. And then we're going to have to add getting a white then a red, which is 2/5 times 1/5. So this is 12/25 plus 2/25, which is 14/25. The last question we're going to answer, what's the probability that at least one ball is white? Now, at least one ball white could be 1 white ball or 2 white balls. So there's actually 3 situations you can do. You can do white then red, plus red then white, then plus white white. Now, truth be told, I probably wouldn't go that direction because anytime I see this at least one, there's actually a trick for figuring out the at least one. So probability of at least 1 is 1 minus probability of none. So instead of finding, which you could go this route, you could find the white-red, the red-white, and the white-white and add them all together. In fact, we already found the red-white and the white-red is 14/25. So really we would just have to add white-white to it. But I want to show you guys the trick where you can just do 1 minus the probability of, we're going red on the first bag, red on the second bag. Red on the first one is 3/5, and red on the back one is 1/5. So 3/5, 1/5. So this is 22 25ths? Believe so. Now, a little note about dependent probability. This is an equation for dependent probability. First of all, the notation, A vertical bar B is conditional probability, and the probability of A, the way you say that in English is the probability of A given that B has already occurred. The formula for it is the intersection of A and B divided by the probability of B. If A and B are independent events, then these four things are true. This might seem kind of complicated, like a lot of things to memorize or something, but notice that with each of them, it starts with the probability of A, and then it's just the probability of A. Starts with the probability of A, it's just the probability of A. Starts with the probability of B, it's just the probability of B. Starts with B, it's just B. So it's really like if they're independent events, it's kind of boring. It's just the probability of the first thing. But if they're dependent events, you really need to use this formula right here. The intersection divided by the probability of the second thing. So there's 84 teachers in a school, and of those teachers, 56 of them drink tea, 37 drink coffee, and 12 drink neither tea nor coffee. We need to figure out how many teachers drink both tea and coffee. Now, for this problem, they don't tell me that I have to write a Venn diagram, but I think it's 100% a good idea with all these problems is to do some sort of visual representation of the sample space. Now, I'm going to show you the way the book does this problem, and then the way I kind of reason through it, but it's essentially the same thing. The way the book does it, well, first of all, we know there's overlap because if you take 56 and 37, it's more than 84. It's like, 93 or something like that. So the reason for that is like if those were mutually exclusive, like if there was only tea drinkers and only coffee drinkers at the school, there would be that many teachers if you add them together, the 56 and the 37. But that number is bigger than 84, which means that there has to be some people that drink both tea and coffee. So the way the book does it is they say, well, let those people in the middle be X. Then the tea drinkers are 56, so this area is going to be 56 minus X, and the coffee drinkers are 37. This will be 37 minus X. And then there's 12 people on the outside that aren't drinking tea or coffee. We know all of those have to add to 84, so you can do 56 minus X plus 37 minus X plus 12 is equal to 84, and then solve for X and get X is equal to 21. I don't necessarily set it up that way. I think eventually I do the same steps, but let me show you guys how I do it. I still start with the 12 on the outside right here. There's 12 people that aren't drinking coffee or tea. So if you take the 12 out of the 84, that means there are 72 people that take up these three regions. So 84 minus 12 equals 72 for, I guess I'll call it T union C. But if you add together 56 and 37, you get 93. Now, what that means is those two circles should add up to 72, but they're adding up to 93. That means that all of these people in the middle have been double counted. So if you take the 93 and subtract out the 72, you get 21. So that means there's 21 people in the middle. And then if you take the 21 out of 56, you get 35. And then if you take the 21 out of the 37, you get 16. Then this is an accurate picture of, of all the numbers of people in each zone. So we're going to use that picture to answer these three questions. Somebody's selected at random, and find the probability they drink tea but not coffee. Now, tea but not coffee, let me get rid of my shading in here. Oh, I gotta really stop doing that. Tea but not coffee. So tea would be everything in this circle, but that includes the 21 coffee drinkers in the middle. So tea but not coffee would be this Pac-Man on the left. Only tea. So this would be 35 out of the 84. Oh, and they want me to use notation. I should. Probability of tea and not coffee. The second part says, if they drink tea, they drink coffee as well. So there's some confusing wording on this. If they drink tea, they drink coffee as well. This is a sneaky conditional probability. They're saying it's given that they drink tea. So they're saying probability of coffee given that they drink tea. Now the formula for that is the intersection of coffee and tea drinkers divided by just the tea drinkers. So the intersection of coffee and tea is 21 out of the 84. So we get 21 84ths on the numerator. And then the tea on its own is 56 out of the 84. So then when you do your multi-flip, the 84s cancel each other out. Remember, if you're ever dividing by a fraction, it's the same thing as multiplying the top fraction by the bottom fraction upside down. 84s cancel out, and you get 21 out of 56. Got that 56. That's it. Part D says, if they drink tea, they don't drink coffee. So this is another sneaky conditional probability because they're saying it's given that they drink tea. So that's the given part at the back. But then they don't drink coffee. So this is C naught on top. So this will be the probability of the intersection of C naught and T divided by the probability of T. I feel like I already found the C naught and T. Yeah, it's this right here. It's the 35 84ths. So the top is 35 84ths, and the bottom I already found as well, which is 56 84ths. Do your multiply and divide, you get 35 56. Can that be reduced? I don't think so. There's the whole problem. Oh my gosh, you guys, that is it. All right, please ask me questions during class.